No. Okay. We'll start the lesson proper. Right. We will hear the last lesson, Kepler's third law. We finished the proof where time square is proportional to radius cube. Yes. So proving, or rather the law itself is not the key idea. I mean, you should know the law, right? That is a given. But it's how you prove the law that is equally important, right? So you let the centripetal force given by gravitational force, Newton's law of gravitation, equal to that of centripetal force. Okay, you'll learn that actually pretty soon when I lecture you on gravitation. Okay, and then you get this. So next, have you all seen this slide? Okay, so what is a geosynchronous orbit? Geosynchronous orbit is a specific orbit, right? It's a specific orbit where the satellite is always above the same point of Earth. And not just any point, but above the equator. Okay? So it also means that the period of orbit must be equal to the period of the rotation of the Earth. Okay. Right, so here we are asked, determine the speed of the satellite in terms of G, H, R, E, and ME. Right, G, H, R, E, and ME. If you know the period to be the same, right, you can determine the speed of the satellite rather easily using V equals to R omega. Right, the velocity of the satellite will be equal to radius multiplied by omega, where omega is angular velocity. Any questions? Right. Right. Sorry, that is for part B. Right, if it's only to be safe. If it's not geosynchronous, how do you determine the speed of the satellite? How will you determine the speed of the satellite? It means it's just orbiting around the Earth, right? How do you determine the speed of the satellite? Well, it's just mv squared over r equals to gmm over r squared, right? The previous equation that we have. So let's see if that's true. Right, mv squared over r being the radius from the center of Earth to the satellite itself. Right, that's on the left hand side, you have the centripetal force equation. On the right hand side, you have the gravitational force equation. Yes? You equate the two, you derive for V in terms of the rest of the symbols that you need. Yep. The velocity is also given by 2 pi r over t. Wait, what was the question? Are we looking for h? Let's look at this. So if you know here that the t is 24 hours, so that means here is roughly around part B already. Right? Here is at part B. You realize this. Something interesting. You have found velocity as a general term. You found velocity as 2 pi r over t. You put these two together, you get this equation. Then you rearrange to find r plus h. And you realize that if the time is fixed, that means if it's a geosynchronous orbit, that means the period of orbit is fixed. You sub in the values, you arrive at this. You arrive at the fixed value. That means all satellites that are doing geosynchronous orbit have no choice but to be at this distance away from Earth. At this fixed distance away from Earth. Okay? Does that surprise you? Somewhat? No. Why not? You already know. How many of you knew this beforehand, that all geostationary orbit? Okay, how many of you knew geostationary satellites? Geosynchronous orbit satellites. What they are? No. Okay. So then it's hard to be surprised because you don't know more about satellites, right? But it should come as a surprising fact if you look at it slowly. Sorry, I have to. This is actually about half an hour worth of lecture in about 5 minutes. Okay, so I would introduce to you what a geosynchronous satellite will look like, right? Then you would think that okay, it could be at any height, but later I will prove to you that actually there's only a fixed height, which should be interesting because what does this mean? It means that we can only have a fixed amount of satellites, right? Before they start piling onto each other and then being shred into parts. But you think about it again in scale, right? How big is a satellite, right? How big is the circumference when you're at this radius? It's going to be pretty big, right? So it's possible to fix in a lot of satellites. And they are not just geosynchronous satellites. Geosynchronous satellites, right, they follow the Earth. So if I have a satellite above Singapore, it will be always above Singapore, right? But there's a disadvantage for this kind of satellites. Because you cannot see what's happening over Africa, USA, China, Taiwan, Iceland, Finland. Oh, wait, Taiwan. Let's not go there. I'm just talking about it in the name, okay? Fine. Right. Let's not get too sensitive. And then you realize that it has a certain fixed velocity. Okay, a certain fixed velocity. Okay. Right, so this is actually example 20. Right, example 20. So I've introduced to you force. Field actually comes rather easily, right? F equals mg. G, that G behind is a field. We have learned in secondary school that G is fixed, but G is actually not fixed. F equals GMM over R squared. If you remove one of the M, you get G capital M over R squared. That will be the field due to the big mass M. So further away you are, the smaller the gravitational field proportional to 1 over R squared. So that's just another part. We will get to that. Okay, don't worry. If you feel a bit lost, don't worry. When we come to the lecture itself, I will go at a comfortable pace for you all. Okay. Next, there's also this idea of gravitational potential energy. We have learned about gravitational potential energy on the surface of Earth. It's pretty simple, GPH. But what about in the scale of planets, right? When your field is no longer constant, GPE will not be mgh because your G itself will not be constant. Okay? There are a few things you want to take note of. For gravitational potential energy, we take infinity to have 0 GPE. And any other value closer and closer to the planet I'm talking about will be a negative value. Okay. But let's look at what we have here. Consider work done by gravitational force acting along a particle moving along path P to Q. Right? As you move along P to Q, the blue lines will be the arrow, will be the directions of the forces. The work done along the radial segment is given by this. The dW, which is the change in work, is force times dr. Okay. So you see that the work done along any arc will be 0. Why? Because it's perpendicular to the F. Right? So any work done perpendicular to the F gives you, any distance moved perpendicular to F gives you no work. Right? Only distance moved parallel to the force gives you some work. To simplify, there is also this other thing. You realize that the work done is dependent on the path and is given by this. What does this mean? It means this. I give you an example. If I move from this point, I give you a very easy example. From this point to this point, I can move in a few ways. I can move from here to here directly. I can move from here up and down. I can move from here down and up to this point. I give you 3 paths. Okay, your friends at home won't be able to see this. But in those 3 paths, the change in potential energy, is it the same? Answer is yes, right? The change in potential energy has not changed from here to here. Why? Right, it's actually because the force you're acting on is a conservative force. Right, it's something that you haven't learned yet. Right, it's conservative force. Right, so if it's work done in the conservative force or conservative field, the path is independent. It's independent of path. The change in energy is independent of path. Okay, and why is that so? It's because of this idea, right? That if you're moving perpendicular to it, there's no work done. Only when you move parallel with it. So all you care is about from here to here is as if it's just moving down directly. Okay, find the radial arcs. Find the two arcs. Just move within these 2 points. From any point within the 2 arcs of the same radius or different radius, it's just that difference. Yeah. In work energy power, we learned that F times distance is work done, right? Force times distance is work done, but that's a simplified version. In fact, it should be the integral of force over a certain distance that is work done. Right? I promise you that this lecture will be harder, and it is right off the start. So the work you do will go into change in potential energy. So this is a change. The work you do becomes a change in potential energy, and the change in potential energy is the difference between the final and the initial energies. Right? So here, you have the standard equation for force. You can then work out, right, using integration and using that first principle of the principle of integral of force dr is change in work to arrive at this equation. Then, because we know that at infinity, the potential energy is 0, right? We can then say that the potential energy at any point r is given by this equation. Okay? In the gravitational lecture that I will be giving you, right, I'll be introducing this equation straight away. I'll be introducing this equation straight away. I cannot and I will not confuse the rest of students by doing all this. Okay? But for you all should know how this is derived. The reason how it became like this is derived from the basic equation of work. I see stunned faces, confused, stressed. Okay, some can. Okay, take some time. But once you have this simple conclusion, things gets a lot happier, right? Just apply this equation, it's a lot easier. Why? You now know that energy is a function of 1 over r. You now know that energy is a function of Earth. Or it could be not just Earth, it could be the Sun, it could be Saturn, it could be any planet, big planets. And M could be a satellite, could be a rock, could be and the moon, right, compared to Earth. Right? You know that energies has this kind of function. So the bigger the big planet center, let's say the Sun, the larger the potential energy of whichever planets that are orbiting it at the same radius. Right. The other point is that energy is always counted as negative. It's always a negative sign. This is quite important. So our potential energy, right, we always say that this water bottle, let's say I lift above this table by 1 meter, is a positive potential energy. How do you deconflict the two ideas? Here I tell you potential energy will always be negative. But here I tell you if I lift the bottle up 1 meter, it's a positive potential energy. What's the problem here? The problem is where you set 0 to be, right? In the usual case, we set 0 to be the tabletop, to be the floor. But here we set 0 where? At infinity. That means maximal height. That means anything below must be negative. Because it's infinity is 0, everything below is negative. Like basement 1, basement 2, basement 3, so on and so forth. Okay? Right. So if we know that there's a potential energy given as such, they ask you what is escape speed. This is an interesting question, right? Because if you want to send a shuttle out of Earth, you must ask yourself, how much energy must I give it? How much energy must I give it, right? Because if you don't do this kind of back of the envelope calculations, you may build a rocket, send it out, it doesn't work, it crashes back, say it doesn't work. You try again with more energy, it still doesn't work. The third time you say like, yeah, it probably doesn't work. Yeah, because you just think it doesn't work. You have not done the mathematical calculation, but it can be done. Right? We have already done it. So let's see how do we know? What is escape speed? Escape speed is a fixed term. You must escape to infinity with at least velocity 0. That means you must escape to infinity with at least some velocity or at least at velocity 0. Can piece the idea together? First, infinity is a strange concept, right? But you are thinking that escape speed is when you reach infinity, whatever that is, you have at least 0 speed or 0.0001 speed. That means you're still moving. Okay? If you do not have enough energy, you will not reach infinity. You will reach a long distance away, but it's a number, and you have reached speed 0. Right? Let's say it's like that. If you move to very far away, you reach speed 0, and then you get attracted back. Right, so I give this example. This is the planet we're talking about. If you throw it with a certain speed, you do this. Boom. Reach speed 0, then get attracted back. Crash back, correct? I throw it a bit more speed, boom. Then get attracted back. I throw it a bit more speed, boom. Speed 0, come back. Correct, huh? And with a bigger bang. So the question is, how much energy must I give it? So let's consider. So it's very same. It's very easy. It's the same as what you have done in secondary school. It's conversion of KE to GPE, GPE to KE, right? So this is the first equation. It looks complicated, but it's actually easy. Okay. The change in KE must be equal to the change in PE. Or in here, it's actually the sum of the mechanical energy, GP and KE, must be equal to the sum of mechanical energy thereafter. Right? At infinity, the K is at least 0. This is the GPE at maximum. Right? You're gonna get this. So actually, if you want to be fast in your calculation, you realize that everything on the right hand side, right from the start, is 0 already. Correct? Right, the first time I introduced it, you were like, wow, so complicated, but actually it's very easy. It's 0 minus 0. No kick. At infinity, K is 0, P is 0. So easy. Right? Which means that now your KE must be equal to the magnitude of the P. Alright? And you easily get this escape speed. So here there's a trick which you will do in your tutorials for gravitation. Sometimes in the question they do not give you the mass of the Earth nor the radius. They don't give you the mass of the Earth. Right? But they ask you to calculate escape speed. Can it be done? IQ question. if I give you the radius of Earth, okay, but I do not give you the mass of Earth, can you calculate for me the escape speed? Right, so you have to link it back to gravitational field strength G. Gravitational field strength G, 9.81, is Gm over r squared. So knowing that G is 9.81, knowing the radius of Earth, you can calculate the mass of Earth, then sub it in. So without giving you the mass of Earth, this is a trick question that they always give. They give you radius of Earth, they say, find escape speed, you're like, what? Okay? Not a problem. Okay, I've taught you that. Alright, escape speed, fun stuff, huh? Earth's escape speed is pretty slow. Yeah, right. If it's meter square, but it's not, it's 11.2 kilometers per second. Is that fast? What's the speed of sound? 330. So it's how many times the speed of sound? Quite a bit. Huh? 30, 40, 30 times, thereabouts. So our rockets that fly off to the moon, has it reached escape speed? Probably not, right? Probably not. Okay, and that is actually a tutorial question in gravitation later on. But let's look at some of the more fun stuff. The bigger planets like Jupiter, right, 60. Saturn, 36. The Sun, 617. Black hole. Black hole, 3 times that power also cannot, right? Right, black hole, the escape speed is so high that even light cannot escape it. And that light is already the fastest thing that we know on our universe. So theoretically, you can reach a stage where you cannot escape something, which is your black hole. It's very cute. Here they say recall from kinetic theory. I don't think you all know yet, but you all will recall soon. In kinetic theory, thermodynamics, you will learn that the energy of a molecule is given by 302 Boltzmann's constant times T. Okay? Which then allows you to find the speed of a molecule at a certain temperature. Okay? Where are we going with this? But if you sub in the temperature of a certain place, like for example, the moon, we can find that we know the temperature of the moon. Yes? We know, we can hence find the velocity of the molecules on it. Right? Assuming we have different molecules like oxygen on the moon, hydrogen on the moon, nitrogen on the moon, so on and so forth. We can submit the various masses. We can find different escape speeds, right? The bigger the mass, the smaller, bigger escape speed. The smaller the mass, the larger the escape speed. The smaller the mass, the smaller the mass, the larger the speed, not escape speed, of the molecules at that temperature. So at Earth now, oxygen is moving faster than hydrogen. Yes? Nitrogen will be where? Faster than? Slower than? Faster, okay. Carbon dioxide? Slower. Okay, the oxygen. But the escape speed of this planet, does it change? Determined on the mass of the particle. It does not, right? It determines only on the G, the mass of the Earth and the radius of Earth, which means that we can theoretically discuss why some planets have no hydrogen, or why some planets have carbon dioxide but no oxygen. Have carbon dioxide or no oxygen? Yeah. Because at that temperature, the molecules itself are fast enough to escape away from the planet and never come back. Whereas the slower ones like carbon dioxide, which is heavy, have slow speeds and hence do not meet the escape speed criteria. Okay? So that's why your Mercury and Moon are airless, because their mass are small, right? The escape speed itself required is actually very small. Okay? I can give you this graph again. Right? You look at escape speed, you can do some back of the envelope calculations on your napkins or whatever, or your letters. Just a random piece of paper, you can find this to be true. Okay, I think I need to move faster. Oh yes. How do we calculate the force with this one is easy, right? G and U. GMM over R square. Divide object into many elements. Yes, this is the one that's going to be difficult. Total potential energy, right? It's the sum of all these different parts together. Right, which allows us to get this. This is the one that's going to get mathematically a little bit challenging. This one is what I already said. There we go. This is the one. Okay. 21 is the one that's a little bit difficult. Calculate the gravitational potential energy of this system. Take potential energy to be 0 when they are far apart. This is not so nice. This question is challenging. So first, we notice that M is right in the middle of the ring, which means that M is of equal distance to every part of this ring. Yes? Right, using Pythagoras theorem, we can say that the distance R is a squared x squared, square rooted. I think in your example, we say this to be S. Okay? So we want to find part A, the GP of the energy of system. We have the distance, using the equation I given earlier for the elements, du equals to all this. Basically, it's the same. It's the same idea as a potential energy. Potential energy U equals to Gm over R. Okay? What you change here, instead of U, you change to du, M, you change to dm, because you want each part of the M, and R becomes this distance. Then you integrate it over the whole mass M. But how do you integrate? Just integrate, because the whole thing itself will be mass M. So mathematically, if you just look at the equations, you do not know that this is actually a ring, It could be parts of masses spread around this dot at distance x squared plus a squared. Right? Spots. It need not be a ring, mathematically. Although that would be a strange thing to describe. Okay. Part B, it asks you what happens when the answer reduces when x is very much larger than the radius of the ring. So it means that as if the ring to Sm is actually like a dot. Right? So it's as if it's two particles. So when x is much bigger than a, right, a disappears, goes to 0, right? It looks exactly like your original equation, which is Gmm over R. Okay? It should satisfy this criteria. Part C, they ask for, use this to find the magnetic direction of the force of the particle. Oh, this is horrible. So you have to differentiate it, which is not nice. Then you'll simplify it to get this. And part D is actually the same as part B. What happens when x is much bigger than a? You get back also what you expect to get, GMM over R squared. Okay? This question will be one of the more mathematically challenging ones. But do not be afraid, you have a lot of this. The more you do, the better you get, okay? Next, part E. What is the value of u when x equals to 0? Very interesting, huh? If the object is right in the middle, is there a force on the object of this pink color mass? It is right in the middle, the force, the gravitational force should be 0, right? Because there's an equal pull on all parts. But is there a gravitational potential energy? The answer is yes. Right, it will be a non-zero answer, right? Because 0 is actually an infinity. So x becomes 0. The energy is actually u naught. Right, we can take it to be u naught. X is 0, we get this answer. Force also becomes this. Not a problem. Explain why it makes sense. Since every point I'm ring, yeah, this is already what I've said already. Any questions? Really? Really, yeah? Okay, ask this one, huh? Why do you differentiate dx? If I given you this as x and this is a, do you still du dx or should you use du dA? Right, it just happens that x I give you like that, ma. Then I say using the equation du dx. You should use du dA, right? But why dA? Why in this direction? Why in this direction dA here? Why in this? If I swap a and x, it will become du dA. Right? But why in this direction? Why not in other directions? Anyone? Yeah, that's right. That's a good answer. Right. In physics, we use symmetry most of the time to solve the question. So seek out the easiest path to get you to the answer. And in this case, this will allow you to. If you solve in differentiate any other direction, it would be super painful. Okay, it will be super painful. No kidding. Now here I also present to you what you would do if you try to calculate force directly. Right? Previous one, I used the understanding of energy and force, right? F equals to du dr, negative du dr. The understanding to link it together. But you can actually calculate force together, the force directly from the original equations that we have, gmm over r squared. Right? But dF is actually dm. right? Integrate for all m. But the problem is actually for this part, the force is actually cosine theta, right? So you need to express cosine theta in terms of x and x squared plus a squared, right? Because the force is actually not towards the center but at the component. You can actually resolve that out. Put it together, you get back what you got just now. Okay? So you can do it in many ways and can check your answers using different methods. Alright. Now for parts that is not in your notes or question, but also is tough. Force due to a spherical shell. How many of you watched Death Star? The Star Wars 7? Not yet. Yes. So whoever watched, in Star Wars 1 to 6, they built the Death Star, right? 1 to 6, they built the Death Star died. I mean, there were Death Stars, which is basically a big planet made of metal that shoots down other planets. In Star Wars 7, there's a Star Killer, which is like much bigger version. But basically, if you can imagine a Death Star size material made of metal, but only on the surface, imagine a ping pong ball but stretched to the size of a huge planet, and you are in the middle, right? What's the force that you should feel? Huh? Downwards in the center? How do you know? Right? Intuitively you are right, but can you calculate that? That is the challenge, right? That is the challenge. Right? If you are on the outside, what happens? And surprise, surprise, the force within the shell is actually 0. Strange. Okay, go look up the derivation. It's going to be very, very fun. And outside, it's as if, right? It's as if the masses were at the center of the planet. Okay, the derivation will be very mathematical. I'm not going to kid you. It's going to be challenging, but it's going to be satisfying. Okay, go and find out. Go and read this out. Okay. Solid uniform sphere. Oh my God. Consider a sphere to be made out of concentric shells. Each behaves as if the mass concentrated in the center. Same applies for the sphere hole. Outside. This is what you will have for a solid sphere. The force you feel actually increases as you move away from the center. Okay? So external of it, you can consider it as if all the mass acts at the center. Within, right? Within, you have to consider only the mass within the radius. So for example, you are at this radius, you are as if considering only the mass here, the mass that you are encircling at the center. So naturally, the further you are, the larger the force. Okay? Because the further away you are, although the R is increased, the mass is increased by Q, right? By a Q. Can process that? Don't worry, it's hinted at in your gravitational tutorial. It's hinted at. Okay? We don't ask the H2 students this. So if this is your force, what do you think the potential energy should be like? F equals to du dr, right? So you can differentiate to find the potential energy to the solid sphere. Yeah, there you go. This will be what the potential energy looks like. Okay? I think the arrow is a bit off. Okay, the arrow is a bit off. Is it? Sorry? This is r hat in the direction of the radius. Unit vector r. This r, his question is what's this r hat, right? It's in the direction of r. Unit vector r. It's a mathematical symbol. So, okay, wait. What's the big R? What's the small r? Right, radius of the Earth. Small r is radius from the center, right? So what you... Are you okay? Sorry? No, not okay. Okay. Ignore this small r. Okay, ignore this small r. If I cover it up, does it still make sense? No, look. This r is not a value. This r is a direction. This r hat. This r hat means r hat, right? Means literally r hat. That's what they say in university. It's called r hat. I'm not kidding you. R hat literally means this force that you have, everything to the left of my cursor now, okay, everything to the left of my cursor now, is the value, the magnitude of the force. The r hat is a direction of the force. That's it. Now, don't confuse yourself further. Okay? You should see this in your textbooks. You'll see your I hat, J hat, and all that. Hats coming out. Alright, so the same thing here, F equals to du dr is r hat in the direction of r. Is it 0? 0 is at infinity. The question is, why is the energy at the center of Earth not 0? Potential energy is not. Because 0 is at infinity. So you have to flip the understanding around. You have to take some time to grapple with that. But mathematically it would make sense. Mathematically it would make sense. Okay, slowly. Take some time, Head is burning already, right? Okay. Don't worry. Okay. Cannot say don't worry. Worry about this, but go and work on it. Okay? It's because I had to shrink so many things down into a very short time. When we have the gravitation lecture, all this should become easier, really. Okay? So painful, right? You got to integrate this whole thing. You get this monster-looking thing. Let's move on. No, don't kill yourself. It's fine. Let's go to simpler questions, alright? Simpler questions. This is in your H2, so you can do it for sure. Okay? Binary system 1. I was told that I think there's a mistake somewhere, alright? So let's look at it. We have two stars. The masses are equal. Orbit of each star is 220 km per second. And the orbital period is 14.4 days. Means what? It takes 14.4 days to move from this spot back to this spot. Okay? Find the mass of each star. How do you do that? Relate circular motion forces to gravitational forces. Right? So you have this GMM over R square equals to mv squared over R. Now, I want you to be very sure what I'm saying. See, mv squared over R, circular motion, mv squared over R, that R is the distance to the center of the circle. Hence, you have only one R here. Okay? GMM over R squared, that R is the distance between the two planets, which is why here is 2R. Okay? Simple stuff. Once you have this, you can rearrange and you find that mass is given by 4v squared R over G. The period is given by the velocity divided by the distance gives you 1 over t. Right? So t equals to the distance over the speed. Rearrange, I was told this is supposed to be 2. Am I right or wrong? Someone told me this should be 2. Yeah, it should be 2, right? Yeah, but I think here is correct again. Right, so here is a mistypo. Ladies and gentlemen, this side is 2, but it doesn't matter. Yeah, I get it back correctly here. Like magic. You put in the rest of the things. Velocity being converted to meters. Time converts to seconds. You find the mass to be 63.5. 63.5 solar masses. What does this mean? 63.5 times the size of the sun. Do you know of anything that happened recently with two things orbiting each other? And then colliding? Two black holes, right? Two black holes. This is what they were doing, right? Given a short enough amount of time, they are actually as if they are orbiting without getting closer to each other. But given a long enough time, they orbit, they lose velocities, they start circling each other closer and closer, and then they collide. Then giving off the gravitational wave. But that's another question, another discussion for another time. Right. Let's stick to the question. If not, we really cannot go home today. Very good. Does the center of mass have any attraction? The center of mass is it's not where the mass is, right? It's the idea of where the mass is. It will hence not have the attraction because it's itself is no mass. Oh? Yes. The two stars are now a different mass, separated by distance d, revolving. Okay, so this is what you actually have in real life. Right? It's very difficult to have two exact same mass planets. Very hard. Right? One has one more molecule, it will already have a different mass. Right? To have exactly the same amount of molecules is just crazy talk. Right? So this is what you actually have. Right? And when you look at this, it's actually very easy to think of it as, you think of it, have you seen skating? Ice skating. Ice skating, the man, bigger size, holds the girl and starts to hold her and he lifts her up a leg and she swings it like that. You know what I mean? But as the guy spins, the guy will be like the blue planet and the girl will be like the yellow planet. These are hands. It will be like that. It's the same physics. Alright, except that the force in the hands is replaced by the gravitational force here. Right, it's the same physics. But of course, when you look at this, the math gets a little bit more complicated. Why? Because you got all these monsters. What's this? Let me try to understand what this is also. RCM equals to 0 equals to MR2 plus M minus R1 over M plus M means that MR2 equals MR1. Yeah. There's a very simple way to figure this out. I give you a simpler, more intuitive way. This is always what I do. You look at the math here, so confusing, right? You just imagine a very light stick in between the two. You have a bowling ball, and here you have an orange. In between you have a very light stick. Where would you place this? Center of moments. Just a simple center of moments equation. Right? It's a center of moments equation. Okay, where this times the mass times the distance is the mass and the distance. It's not that much hard. You can skip all this difficult math and just get straight to this. Both R's are in referral to the center of mass.
So that's how that's how.
No, magnitude. Just the value. Just the value. We take from center, everything outwards is positive. Just a positive value, no negative R. All R's are positive.
Negative R.
I'll figure that out with you later. This equation is kind of interesting for me also. No, this is the counterclockwise movement. Negative because it's counterclockwise. Yeah. There, figured out. Once you have this, you can start with these two. You have these two equations, right? The gravitational force on this side, the gravitational force on the right hand side. Centripetal force. Instead of using centripetal force as mv squared over r, we use mr omega squared. That is the other form of centripetal force. Right, there's mv squared over r for centripetal force or mr omega squared. These are the two forms. Choose one. In this case, we use mr omega squared. Why? Right, you realize that omega can be given as this, and they can be given as this, and it's equal to each other because they are circling each other. If the omegas are not the same, one planet will catch up with the other, right? Then the center of mass will no longer be here. Right? Then this is not a binary system. So you have this criteria that you must put in, which is here. Which then allows you to say that since the omegas are the same, their periods are the same. If their periods are the same, we can then say that V1 over V2 equals R1 over R2. Because V equals R omega. How do I get this? How do I get this? How do I get this equation? Take the first equation, simplify, remove the m here, remove the m here. Take the second equation, remove the big M here, remove the small m here, add together. You get this. Okay? But once you have that, what can you do with it? Alright, you can find the period to be this value. At this point, a lot of students will ask me, sir, why do we not just find the period with just one of the masses? Right? You look at this equation, you can immediately find the period already. Do you agree? Look at this equation at the top left, you can already find the period. Yes? 2 pi over t, certain radius. But it's because if you do that, you have a certain radius here. What if you are only given d itself, the distance between the planets, and not the radius of R? Right? So essentially what we have here is a simplified equation where we only need to know the distance between the planets. Okay? If you have the radius and then the centripetal motion, then yes, you can just give it in terms of R1. Using this, you can get it in terms of R1. Okay? Right. Let's pause the video here because if not, they will die from